Well, now it's time to start the course off. This is Lecture 1. It's going to be an overall introduction to the course. And the first lecture will be very high level. There won't be an awful lot of math in it. And it will give you just a very quick, broad overview of radar and the material we're going to cover in the course. Then, as I said earlier, there'll be 2 lectures that will review certain material in electromagnetism and systems and signal processing, digital signal processing, that are extremely important and they'll be used in the course, those concepts. And then we'll dig into the heart of the material starting with Lecture 4. And that heart of the material is going to be lectures 4 through 17, which I call the core material of the course. Okay, so let's start off with the introduction. The introduction will be divided up into 3 parts: background material, the basics of radar, and then the course overview. Now, this is the material that we're going to discuss in the background. We're going to go over some pre-radar history of how people used what target detection methods were used before radar. We're going to talk about how radar works in one simple view graph, so you can say, oh, now let's go on. And then we're going to talk about the early days of radar, how it was invented, why it was invented. And to stimulate and motivate you as students, I want to point out 2 examples from World War II, when radar was first developed for operational use, that made really big differences in the outcome, both from strategic and tactical points of view. And I'll bring in some first-hand knowledge that I have of people who actually participated in those things, and also a lot of historical reading that I've done, reporting on that material. And you'll see, wow, radars really made a difference in that war. And these are only 2 examples. I could probably, and I will name off quickly, half a dozen others that I could talk for an hour or 2 on. And then we'll go into the other subjects. Now let's start off with some pre-radar history. Well, if you think about war, it's all about knowing what the enemy's going to do ahead of time, knowing what the enemy is doing, and being able to counter the enemy and see how well your attack is doing, the difficulties it's having. It's surveillance of the battlefield, reconnaissance of the battlefield, what we call today situational awareness, understanding what's going on. And I think it was General Eisenhower who said, before war, plans are everything, but once a war starts, throw out the plans. That's my interpretation of those words. You know, it's about what he said. And that's what happened, of course, at Omaha Beach and D-Day. They thought they'd be many miles inland, and they had a very brutal, hard time on Omaha Beach at D-Day in World War II, getting ashore for a large number of reasons. And on Iwo Jima, there was just no way that they had of knowing how entrenched that the Japanese were, as you can see there on the island of Iwo Jima in Mount Suribachi, and how difficult and devastating the attack would be. And so the less uncertainty there is, the better you like it if you're a commander of war for your troops and for the outcome of the battle. Now, before radar, a lot of different sensors were used to detect aircraft and to detect attacks from the air and the ground, for that matter. Here we're focusing on air attacks. Optical systems were used quite a bit. Searchlights were used in the 30s and 20s, and you can see here This is actually around Gibraltar. It's a photograph courtesy of Great Britain. A lot of the World War II photography that was taken by the British government has passed the copyright age, which is somewhere up in the 40s or 50s of years, and it's now all in the public domain. This particular photograph is was taken by the British government. And here's another one from the National Archives. Just a plain old fellow on top of a building with binoculars. Here's, I think, St. Paul's Cathedral in London. But the optical systems have some significant problems. There's attenuation by the atmosphere, and there's significant range limitations. And because of the nature of the wavelengths, you can see there are very narrow fields of view. It's hard to see over a wide field of view, and that's caused by, as we'll see later on, caused by the very small wavelength that optical radiation is. And then there's the issue of cloud cover. Light won't allow you to see through cloud cover, and worldwide, 40 to 80% of the time, things are covered. If you look up at a certain point in the sky, there's clouds in the way of where you want to see. To give you a worldwide view of that, this is a NASA photo of a study that was done over a period of many years in the 1980s, looking at total cloud cover in the world. And you can see that a very large portion of the time, here's the percentage of the time that the radiation's opaque to cloud cover. And excuse me, this is the percentage of the time that you have cloud cover, and you can see that it just there's not a lot of the time that you have cloud-free line of sight that you can count on. And both infrared radiation and optical radiation are opaque to clouds. Now, people also use sound. If you live near an airport, hopefully not too near, and you can hear a jet plane that's 25, 30,000 feet up in the air. Where I live, it's near a major air base, and not too near, but when jet planes are flying 30,000 feet above, you can easily see them, and if you're driving even several miles from the airport, you can hear them coming. And in the first half of the 20th century, the military of many nations, the Japanese, many European nations, here are two U.S. Army acoustic detection systems, developed systems that, again, were limited in range. The sound doesn't travel that far, even from a very noisy jet plane. You know how loud it is when you get up, enter a jet plane and the jets are idling even. It's extremely loud, but more than 10, 15 miles away, you really can't hear them. And so the range is quite limited. And again, these are directional sensors, and the ambient background of weather, lightning, storms, wind in the trees that's nearby, all contribute to limiting the range. And these were used in the first half of the 20th century along with searchlights at night. You notice, particularly in these systems, it's easy to see that there was sort of an antenna listening above and below, and from an operator over here with earphones measuring if this signal was higher than that signal, they knew that they weren't pointing exactly at the angle of the planes, and so they could adjust on azimuth or elevation the instrument and get the right directionality of where the aircraft or group of aircraft were coming from. Over in Great Britain, just before World War II, the British got quite serious because this is what they saw as, gee, this is all we've got. And they built huge sound mirrors. And this is in Kent, in the UK. These are the remnants of sound mirrors that were built a short time before World War II. And even with a 200-foot parabolic receiving aperture where an operator would sit at the foci of the parabola or at these here, the operator would sit right there at the focus with earphones listening out, the detection range was less than 15 miles. Now, even during World War I, if you could hear a British Zeppelin, like a blimp, 15 miles away, it was only moving 10, 15, 20, 30 knots. It would give you some warning. But with faster World War II German bombers, these kinds of technologies just wouldn't cut it at all. This shows you how radar works. It's really simple, you know. A pulse of electromagnetic radiation is transmitted by the radar. It's given directionality by an antenna. And of course, each of these words I use, like directionality of an antenna, there's going to be a whole giant lecture on each of these pieces. The electromagnetic energy will hit a target and scatter off of it. Some of the energy, with a different color, will scatter back out in all different directions, but some of it will go back to the antenna. It will be received, listened to, and the difference in the time it takes, the round-trip time it takes for the electromagnetic radiation, will give you a measure of the range, because the electromagnetic radiation is traveling at just about the speed of light. And so the time difference will tell you how far things are. And here's the equation. If this is the round-trip time the round-trip time, it's twice the range to the target over the speed of light. Okay. Now, as I said, trust me, it's going to get more complicated, and that's why I gave you a preface up front. This is a very quick overview. Now let's talk about the early days of radar, how it all came about. Radar experiments were being done, and the principles of radar in many different places. And different people contributed in different experimental groups in the 1920s and 30s, got to understand that that when they were using their communication systems and an aircraft would get in the way of the communication system, they would notice a scattering, an attenuation, a disturbance of the received signal by the target. And then they got the idea, hey, some of the energy comes back, and I could understand the distance away of that target. And scientists, I believe it was at the Naval Research Lab in the United States, could tell when ships were passing by a communications site on two different sides of the Potomac River, I believe it was, that the ship was passing by from the change in the signal. Many consider Sir Robert Watson Watt in Great Britain as the inventor of radar. He actually was granted a patent in 1935, but the significant work was done in many other countries. And Britain, because they were so close to the Nazi threat of Germany, that they worked hard to develop radar into an operational system. And they were way ahead of anything that was going on in the United States in the late 1930s. And he led the development of the first radar air defense sensor system. And it was called the chain home system. And it had an adjunct to it, chain home low, went after low targets. We'll see about this in a minute or two. And a host of other radars that were developed by Great Britain at the very beginnings of the war, and were under development there. But in the 1939, early 1940, Great Britain and the United States realized that Great Britain could indeed be overrun, and so they sent over a mission with one of their scientists, Sir Tazad, and he brought over with, I think it was 7 of their experts, this famous box full of equipment. We'll talk about that in a minute. That contained some of their recent inventions that were revolutionary to radar. And that use was magnified. Here's a picture of Sir Robert Watson Watt. Now, I mentioned the Tazad Mission to the United States of their scientific and technical people. Yes, it was 7 radar experts and a black box. Now, in that black box was everything they knew about radar and an incredibly interesting device called a cavity magnetron. It was a way of generating electromagnetic energy at short wavelengths, 10 centimeters, about that much. Up till that point, the chain home system was using magnitudes more wavelength, and that made the antennas much, much larger. The practical antennas were much, much larger, and, for instance, couldn't be fit on airplanes. And so possession of this cavity magnetron technology turned out to be critical in helping jumpstart the American war effort. And when this stuff came over, now this is a photograph courtesy of a colleague of mine, Eli Bruckner, that he took when he was over in Britain. This is the original 10 kilowatt pulsed magnetron for 10 centimeter wavelength. It's the original one. I believe he took that photograph in a museum. And then the United States realized the importance of what was going to happen, and they formed the radiation laboratory at MIT, where a huge amount, we're going to talk about that in a little bit, a huge amount of radar research and development was fielded. Now, the radiation lab operated between 1940 and 1945, and it was one of those tremendous efforts that a country puts on in wartime. We all have heard of the Manhattan Project, where the atomic bomb was developed, and it turns out, well, if the country's university professors realized you were really, really smart in science, physics, and engineering, or chemistry, or the field needed, you either went to Los Alamos and were working on the atomic bomb, or you went to the radiation lab, or also to Johns Hopkins Applied Physics Lab, where some fantastic work was done in proximity fuses, which we'll get to in a minute also. At the radiation lab during the war, many, many radar systems were developed and fielded for the first time for war use. This was serious business. The world was at war. And they exploited that 10 centimeter wavelength cavity magnetron invention. I'm going to show a system that does that. And the laboratory grew. And just imagine, the whole length of the rad lab, as it's called, was the order of 5 or 6 years. It grew to 4,000 people. And to give you an idea of how bright these people were, 9 of them went on to receive Nobel Prizes, most in physics, some in other fields. And a lot of the original people in the rad lab were physicists, an awful lot of engineers. And they designed almost half the radars in World War II, more than 100 different radar systems worth $1.5 billion. They'd build the first one, test it out, and then it would go out to a newly created company who would build hundreds of them for the field. And this is the home of the MIT Radiation Lab. When I was an undergraduate at MIT, this was the Sacred Building 20 many of us did research in, and the home of many great, after the war, many great technology developments at MIT. Now it has been taken down, and a multi-story modern building for all kinds of new and great research has taken its place. And here's a photograph of one of the, I would say, one of the most prominent radar systems that was developed during World War II. It was called the SCR 584. We're going to talk about that in detail. And that is indeed a 10 centimeter magnetron radar. I might add that radar development had been going on starting in 1940, and much to the chagrin of people afterwards, one of those radars, an SCR 270, I believe it was located on Oahu on Opana Point, north of Pearl Harbor, which was in the south, and it detected 55 minutes before the attack on Pearl Harbor, it detected that fleet of aircraft coming to attack Pearl Harbor. The operators of the radar recognized it as what they call a blip on the screen. No digital CRTs like we have today in our computer systems. It was just a little bump in a CRT, but they recognized it as a huge signal that was traveling at the airspeed you'd expect aircraft to come, and it was coming from the northeast. And that was the direction. They immediately sent forward the information to a control center, which was unfortunately an inexperienced lieutenant was at the center. It was, we all remember, a Sunday morning, and he just said, it's that fleet of B-117s, bombers coming from the West Coast that we expect sometime this morning. And indeed, it wasn't. I read the congressional testimony in the hearings afterwards, and it was one of those things where human beings make a mistake, and we actually would have had a 55-minute warning of the attack if that radar detection had been taken seriously, sent down the chain of command, and general quarters were taken. There would have been obviously serious damage to the battleship Roe, but how it would have changed it, we'll just never know. But the attack was detected ahead of time, and obviously in the aftermath of Pearl Harbor, radar was taken very seriously, very quickly. Now we're going to look in detail at two examples during World War II of the impact of radar on World War II. And the first one I used in an earlier video. The second one is a new one, and I'm just going to mention briefly some other examples where radar, just say the words in a sentence or two. The first one was in the air defense of Great Britain during the Battle of Britain in the summer of 1940. I want to set the stage for you. World War II has not yet started. France has fallen. Dunkirk has happened. The Lend-Lease program has started, and we are pouring what supplies we can into Great Britain. Britain's army was defeated, along with the French, and the orders of 100,000s of troops came back. Many were captured. Things weren't good on the British Isles. They were very concerned about invasion. And the obvious point, which the Germans were planning to come across and building up a fleet of barges, was at Dover, where from the cliffs of Dover you can look over, and 12 miles away you can see France. And we're right now, we have the tunnel that goes from Great Britain to France, and you can go under the tunnel. They were very close. And what the Germans had to do was achieve air superiority over Great Britain. The reason they had to achieve air superiority was if they didn't have a great fleet of battleships and cruisers anywhere near the great fleet that Britain had, which they kept in harbors up in Scotland and relatively free from air attack. They weren't that vulnerable. They were relatively safe. But if a landing was started, which would take a day or two or whatever, there was plenty of time for this fleet to come down and sink the invasion fleet. And if Germany had air superiority, it knew it could sink the fleet when it came out into open waters. There had been many instances where the Japanese had sunk British capital ships in the Pacific. People knew that airplanes could sink capital ships quite readily. So the Germans had to get air superiority. And also, they were bombing Britain, and they wanted to bomb it into submission. And so what the British did was set up a system of radars. Initially, there were 21 early warning radars, and I'm going to explain what they were and how they worked. The remnants of these radars, their transmitting towers, still exist over in Great Britain. Many of them are used as cell towers. They were made of steel. They're several hundred feet high, and they came in triplets. And as you see, I explain the antenna system, you'll understand. This photograph is courtesy of Bob Cromwell, who took it in September of '06 on a trip over to Dover. And it was the antennas, which I'll show you, are hung between the towers in a moment. This was the site at Dover. And this was their line of air defense so that they could tell if they were being attacked. Well, why was this important? I'll tell you it right up front. The Germans had about 1,500 fighters and pilots. The British had about 1,500 fighters and pilots. And they would come in from captured France or from some direction. They'd come in a vector, carefully concentrated, to go in and out quickly. Remember, this distance is just 12 miles, 15 miles. So it's a very small distance, and the planes typically will go 250 miles an hour. So they could go in, drop their bombs, London's right here, and get back home without Britain being able to focus in that one place their fighters to knock down the bombers and to fight the fighters and do battle. Because they were too thinly spread with all their scattered airfields. And they had to be scattered, or if they were in one lump place, they could be attacked and destroyed on the ground. Now let's look at the air defense radars that the British built. These used the technology of the day, very long wavelengths, 10 to 15 meters, and frequencies between 20 and 30 megahertz. So 30 feet to 45 feet was a wavelength. And dipole antennas can be built at a half wavelength. And there's a string of 8 dipole antennas. We'll look at this is the transmit antenna, and another string of the very dark lines of the active elements strung between the towers. And the antennas were built in duplicate for backup. And then these were made of steel, and then a set of wooden towers that held crossed dipoles, high and low, which were used to receive the backscattered signal. The beam width of the pattern of this was about 100 degrees. You say, gee, 100 degrees, how can you tell where anything is? We'll get to that in a minute. They operated at a peak power of 350 kilowatts, developing all the peak power they possibly can. The point is, they could detect at approximately, at high altitude, that'd be like 20,000 feet for them, at 160 nautical miles, a Junkers 88 German bomber. So they could see the bombers coming if they were coming high at 160 nautical miles. Okay. This artistic visualization was developed by an artist, Chet Beals, in MIT Lincoln Laboratories Graphic Arts Department, and he developed it from a British paper which described technically what the system looks like. And I could not find anywhere a really good visualization of what the chain home radar looked like. And from that technical paper, which has very crude drawings, not at all to this beauty, this drawing, and with permission of MIT Lincoln Laboratory, we're allowed to use it. And a British radar expert, has told me that this is probably the best visualization of the chain home radar system that he's ever seen. Now here's a picture, what I call a technical picture of the radar. The elements were, you see these dark elements were half a wavelength long. To get more gain, directivity in the vertical direction, there was a row of them, 8 of them, a half a wavelength apart, and then a gap filler antenna to make a beam at a lower angle. And they were up at, the tower was steel and 360 feet tall. And then one of the received towers, here's just one of them we've visualized here, they were wooden and 240 feet tall. And what they would do is they would receive the signal with a cross dipole at 95 feet and 240 feet, and look at the phase difference of the signal in altitude with one set of receive antennas. And they had, of course, 4 of them, as you remember. I'll go back just for a moment. They had them side by side, and they'd look at the differences of the signals from the side-by-side reception and the up and down reception combined to look at that phase difference to tell where within the 100 degrees the flight was. So they could, so to say, split the beam down from 100 degrees to the order of 5 degrees. So they could do 5 miles or so. And they could tell to about a 5-mile by a mile or 2 or 3 section where the attack was coming from. And that was fantastic to know. And let's look at a visualization that will tell us first what these pictures looked like. These photographs became in the public domain, I think it's somewhere in the 40 to 50 years after they were made. These photographs that are black and white are courtesy of the United Kingdom government. They were all taken by British military people, and all photographs taken by British military personnel after 40-something years become in the public domain. So it's now we're able to see them. And here is a female operator looking at a oscilloscope, looking for those blips of where there was a received signal, measuring the range with templates. And here is a device called a goniometer. And by twisting that goniometer so that there was a balance between the upper level of receive and the lower level, and the right and the left, one could do the beam splitting. And here's a picture blown up a little higher of the receive huts. They were located mostly below ground and battle hardened. And then they would take that information. Oh, and by the way, up here is a picture from a museum in Great Britain of the chain home transmitter itself. And here is a plot room where the receiver operators would plot the position and range, would send the position and range and azimuth to a station, which would be the command and control center for the site, and then to an air operations group where they'd have little markers on a giant map of the lower section of Great Britain showing the progress of the attack, and then via telephone lines alerting the British fighters where to go to meet the attack. So that, this is terribly important, so that I'll get to that in a minute, so that they could focus their attack and have even parity with their fighters and the British fighters, and we'll get to the results in a minute. One of the things we'll go over in propagation is when you have very long wavelengths like this, like the chain home, there are at lower elevation angles gaps in the coverage. And the British built a higher frequency at 200 megahertz as opposed to 20 to 30 megahertz system of radars with the new technology that was being developed to fill in low elevation coverage at less than 2-degree elevation. And they could detect at an aircraft coming in at 500 feet at a range of 25 miles. So they were continually, during the process of this, from the summer of 40 to September of 1940 was the real crux, hard part of the Battle of Great Britain. They were continually upgrading that radar system to fill in the gaps in the coverage and add lots of new radars at frequencies that got up into the S-band region and had ground control intercept radars, etc., which you'll learn about. So it was a continual system of making the air defense system more modern. Now here's a map. I showed you earlier the same map of Great Britain with 20 radars, and here's what its coverage would look like with about 160 miles of coverage. And you could see that it turns out there's plenty of time to see them coming. And I go over here, the logical progression that I went through with you. The radar was what I call a force multiplier. With airfields scattered all over the place, they were able to use radar to concentrate their defenses right at the location of the German attack and focus their limited number of interceptor aircraft so that they could achieve numerical parity with the attacking German aircraft. The effect on the war was that Germany was not able to achieve air superiority, and the invasion of Great Britain was postponed indefinitely because they could not. Now, that allowed, over the next 4 years, Great Britain to be that island of democracy where huge amounts of material from the factories, the war factories in the United States, and men, millions, could come and use as a staging area for the attack on Europe. If that attack had to come directly from the United States, it would have been far more difficult a job, and it just made a big difference in the war, you can see. And now what I'm going to do is take a quick break and then go to the second example of radar in World War II.